Section 6.2 in Chapter 6 is called electrical losses. And he tells us in this section that there are three types of electrical losses. There are what are commonly known as I2R losses or copper losses. These are the result of current flowing through a wire. And anytime, of course, current flows through a wire, there's going to be losses. And there's a way that we can quantify that, and we'll look at equations 6.1 and 6.2 in regard to that. Then there's also brush losses, which really, are only going to apply to these DC machines that we're looking at. As we get into AC, we'll see that won't be a consideration. And the third type is iron loss. So we're going to look at each one of these individually and spend a little time understanding exactly what's going on with those. So here's our three losses listed over here in the on the left side of this screen. The I2 are copper losses, brush, and iron losses. Now, as we go through this, he breaks down each one of these and goes into a little more detail. And the first one he goes through is the conductor losses, or these I2R losses. They're not necessarily have to be copper, would they? I mean, we think about that because that's by far the dominant type of material used for conductor construction. But the losses in a conductor depend upon its resistance and the square of the current that it carries. Okay, I2 are losses. So the resistance then, if that's the case, is dependent upon the things that are given to us in equation 6.1. And this equation is comprised of course, R in ohms for resistance, L in length of the conductor in meters, and area in cross-section in meters squared. This is the resistivity in ohm meters. And it is characteristic of a certain material. And so what we would need, to find that is some sort of table that would tell us that for whatever material, this is the resistivity for that particular material. And then the other thing that we need is something called the temperature coefficient of resistance at 0 degrees. Okay? Now, the resistivity and this temperature coefficient can be found in this appendix that is AX2. Now that's AX1. Okay, so AX2, and I'm not exactly sure what page that would be because I'm showing around 910. It's in the back of your textbook, but resistivity is in this column here. And you can see that what they've done here, this is nano-ohms, okay? Nano-ohms per meter. And now in the text, he just says ohm meters, but nano-ohm per meters. And what he's trying to do is get rid of that very, very small number, that you're dealing with. So for aluminum, it's 26 nano-ohms per meter. And then as you can see, at a different temperature, it's temperature dependent. At a different temperature, it increases, right? And so when we're looking at copper at 0 degrees, and copper is the one we will see the most, we see that it is 15.88 at 0 degrees and increases to 17.24 at 20 degrees C. And then there's also this temperature coefficient that we can use to account for the change in the temperature that we're dealing with and sort of reference it to a norm, okay? And we can see that those values are given. And so that table would have to be given to you. Those values would have to be given to you. And we'll also reference this later on for some other things in terms of mechanical properties and thermal properties. And especially here, this specific heat is something that we'll deal with directly. I think we actually do that in this chapter. Okay, so that's where that would come from. And so when you're looking at this section and you're wondering, you know, where does he get all this stuff? Where does it come from? That's where it comes from. And, you know, we build off of that in these equations that we have. And, you know, that's what we're dealing with. And then, you know, what 6.2 does, you know, it develops this resistivity, and it bases it on the resistivity at 0. And then see, this is that temperature coefficient. And it is, again, is unique to the material that you're using. So, you know, we reference it initially at 0 degrees, okay, right here. And then we adjust it based on the temperature coefficient. And that's how we ultimately end up with this that we can plug into 6.1. Now, sometimes to make this, you know, maybe a little more complicated, but it shouldn't do that. Sometimes we want to express the losses, you know, based on the heat that's generated in terms of the watts per kilogram of a material. Okay, so what we'll do is we'll sort of use some of these same ideas, but instead of expressing it in terms of the length of a conductor, we're going to express it in terms of the weight. Okay, well, actually it would be the mass, wouldn't it? But anyway, we want to express the losses in terms of the watts per kilogram of conductor material. And then we'll look at an actual useful use of that. And so that equation 6.3, and I'll write it up here and then we'll come back to it in a minute, is given as this equation. And then I think as we work through a couple of problems, now again, this looks like that J number from chapter 3, but it's not. It's something called current density. And here's resistivity. And this is all divided by lowercase zeta, which I'll try to draw here. Okay, but you can see that is equation 6.3. And let me just table that for a second, and we'll come back to it. And when we put some numbers in there, it'll make more sense. He says, looking at that equation, the loss per unit mass is proportional to the square of the current density. Woo! You know, that gets pretty removed, but we'll put some numbers in here and hopefully it makes sense. And then he references current densities for copper conductors, you know, and the corresponding losses and so forth and so on. And so the higher densities require more cooling to prevent a heat rise. Let's see, anything else here? Going back to these two equations before we actually plug in and work some problems. DC motors and generators, copper losses always occur in the armature, the series field, the shunt field, the commutating poles, and the compensating windings, okay? All of those things have copper losses, and these losses show up as heat, causing the temperature conductor to rise beyond the ambient surrounding temperature. And so, you know, that's kind of what we're working on here, okay? Now, I know right now this seems a little, you know, a little abstract and all that, but let's put some numbers with this, and I think maybe it'll start to make some sense as we move through this to the next stage here. Okay, we'll stop this video and make a second one and address the topic of brush losses and iron losses and work at a problem.